It's associate scientist.
Okay, so it's a PhD candidate and associate scientist?
Mm-hmm.
Cool.
That's right.
Perfect. Just like two.
No worries at all. Just want to test if this works. Cool. Loving this now.
Actually, then, just run the restroom real quick. I'll be right back, and then I'll
Go ahead. Thank you.
All right, good afternoon, everyone. Thank you so much for joining us today. So I'm very happy to introduce Mike Cohen to everyone. Mike is a PhD candidate at Arizona State University and also a research scientist at Aptima. I think we came to know him as an area group based on some of the panels that he's put together recently at HFES on teaming and automation. Very excited to hear about much of that today. Just a couple logistical things, I think, for folks. Number one, Mike's just asked if there's clarifying questions, please ask them during the talk. But for more in-depth technical things, to just kind of hold those off to the end. Also, if you are asking a question, just would encourage just waiting for me to come over with the microphone. We are recording the talk today, so if it's not into the microphone, it won't get picked up on the recording as well. So with that, Mike, take it away. Thank you.
All right, thanks. Can you all hear me okay? Perfect. All right, thanks so much, Tony, for that introduction. And everyone, thanks for being here and for the privilege of getting to talk to you all today. My name's Mike C. Cohen, and I'm really happy to be here and talk to you about my research on interaction-centered design and evaluation for system trustworthiness. Before I begin, I do want to give a quick disclaimer that the views and opinions I'm about to share are my own and not representative of the official positions of the Department of Defense, the Transportation Security Authority, Arizona State University, or Aptima. With that, let's get started. First, here's an overview of today's talk. I'm going to start by giving a background of my overall research over the last 5 or so years, Then I will discuss some more in-depth empirical works that are central to this concept of interaction-centered design and evaluation. Towards the end, I want to give a sneak peek on how this can be applied to create domain-specific experimental test beds, as well as some future directions that I would love to take this work. And throughout this talk, I'm going to pause periodically in case there are any clarifying questions, like Tony said, but I'll make sure that we have enough time at the end for some Q&A for in-depth conversations. And if there's any questions that arise after this, please feel free to contact me offline. So my current research started around 2020 when I joined Arizona State University's Center for Human, AI, and Robot Teaming, or CHART. At CHART, I've been able to work on some really interesting collaborations across academia and industry. And this started with creating experimental test beds using commercial games like Minecraft and Roblox for running remote human subjects experiments. So the year I joined ASU was 2020. It was in the middle of COVID, and I was stuck in the Philippines for the first full year of my PhD. So remote subjects research, yay. After moving to Phoenix, though, I focused my work on exploring language-based measures for how people trust or personify their AI teammates in simulated drone operations. And all of this work started the foundation for my current theoretical framing that when people and AI interact with each other, they have what I call teamness, which is basically a set of collective qualities that emerge when, again, people and AI interact together towards a common goal, just like how human teams function. And so around 2022, I also began working in industry with Aptima, which is a federal contractor based in the greater Boston area. And my first significant work with Aptima was to develop a tool called Clairvoyant for running on-demand meta-analyses to inform experimental design in human AI teaming experiments. So these were mostly for some DARPA-funded projects. And another of these DARPA efforts included a collaboration with computer scientists at Carnegie Mellon to explore creating purely simulated data sets of how people and AI socially interact with each other using large language models. And most recently, I've relocated to the Las Vegas area to support Aptima's operations at the Nellis Air Force Base. I am their on-site scientist, where I work with the Air Force Research Lab to design and conduct experiments to evaluate some of the most complex AI decision support tools that I have ever seen. And I'll elaborate on that a little bit later. For today, though, I'll be focusing most of this talk on dissertation work that I've done with ASU's Center for Accelerating Operational Efficiency, where I've worked on several projects with the Transportation Security Authority, or the TSA, on exploring the trustworthiness of AI-enabled decision support systems. And at the core of my research at CAOE has been this question: how can the design and evaluation of human-AI interactions enable trustworthy work systems at scale? I'm going to be highlighting a couple parts of this, beginning with work systems. And to illustrate what I mean with this, let's look at the example of airport security as a work system. So airport security has changed a lot over the last few decades. When I was much, much younger, airport security was less intense. Airports were a place where you would go with family or friends, even if you weren't really flying with them, or even if you were flying alone. And legend has it that security lines were not that long, and that it was mostly dealing with nice security staff. But we faced increasing risks with air travel and resulted in the creation of agencies like the TSA. And with it, the modern pre-boarding screening process that a lot of us have become more familiar with than we'd like, I think. Since then, a lot of the changes in airport screening has been in how manual the process is. And this is really apparent in ID verification gates, which face recognition in AI tech has significantly transformed. Now, as growth in computer vision capabilities have really improved AI face recognition, we now have ID verification gates where you don't even have to interact with a TSA agent at all. I want to emphasize two things about this. First, these verification gates without TSA agents, they wouldn't be there if they didn't meet a certain level of reliability that makes them acceptable for this very safety-critical task. But also, a big motivation for a lot of these advancements in incorporating automated biometric systems is efficiency. It's to accommodate growing passenger volumes for aging airport infrastructures. Now, does that make these newer systems more or less trustworthy? It really depends on how you define trustworthy. For me, it means simply whether something or someone, or in this case, a work system, deserves trust. And I consider trustworthiness along 4 dimensions. First, you'll see effectiveness and efficiency up on the slides here, and those are really familiar engineering goals. It's about producing intended outcomes in an economical way. But when you have these safety-critical systems that are fundamentally human-centered, ethicality matters. The decisions that are made in these systems impact people. You can make the false accusation that someone is pretending to be someone who they're not, and that will be pretty stressful for them. And it doesn't just affect the people on the receiving end of AI-enabled recommendations. It's also the people making the decisions in the first place. So that's why equanimity, which in many ways is like the cognitive resilience of people in the face of success or failure, really matters, because these work systems influence how workers are stressed, how their workload emerges over time, and how they perceive their job satisfaction if they want to keep continuing these kinds of works. And last, that leads me to the role of interactions, which are the primary way by which people and AI fulfill the purpose for why these human AI systems are created in the first place. So this means that each of the dimensions that I mentioned earlier are properties that don't reside just in individual system components. They are things that emerge while interactions take place. So in my research, I try to go beyond whether people trust in AI or whether people should be trusted with AI in the first place. Don't get me wrong. Those are both very important questions that I still explore in my research. But I believe that it's important to also focus on how we can design for and evaluate whether we can trust people and AI as a collective, as they interact and work together. So for the next few minutes, I'm going to be diving deeper into some empirical works that started this focus on interactions as the unit of system trustworthiness. And I'm going to begin by hopefully showing you that strengths and weaknesses of people and AI at decision-making are inextricable from the way we design the interactions that they have with each other in these applied work environments. But I'm going to be pausing here in case there are any quick clarifying questions. All right, seeing none, I want to go back to my example of ID verification at airports. The human AI work system here revolves around a task that we call face matching, and this usually follows a few steps. First, you give your ID to a transportation security officer or a TSO. The TSO scans your ID using an automated face recognition system, and that system tells the TSO on their screens if the face on the live camera feed matches the picture on the ID that you gave them. Now it's up to the TSO whether they're going to be sending you off to the exciting land of baggage screening, or if they're going to be exposing or subjecting you to additional screening procedures. This is very situational. It really depends. And later I'm going to show an example where this is not really that straightforward to begin with. But in general, there's a very linear path that this work system follows. One thing to emphasize here is that face matching is fundamentally a different task depending on whether it's performed by a human or if it's performed by an AI. And for people, it's actually pretty cognitively challenging. And so one of the first studies I did was to understand the relative strengths and weaknesses of people and AI at face matching tasks, and how we can use that as a foundation for building trustworthy ID verification systems. And I did it this way. So I worked with a fellow graduate student at ASU to gather more than 2,600 image pairs from 13 public face databases. And we worked with a computer science PhD student to assemble 3 Siamese network models. So these are convolutional neural network models that, at least at the time, were state-of-the-art for the face recognition task that we had. These were trained on hundreds of thousands of these image pairs specifically for face matching, and allowed us to identify, because we knew the ground truth, which pairings of images were the most challenging and the easiest for our assembly of AI models. And that helped us down select to a subset of face matching tasks for Amazon Mechanical Turk participants so that they would face match it and annotate relative to their own demographic profiles. At the end, I developed structural equation models to create a profile of human and AI face matching performance using signal detection theory, and I was focused on 2 types of errors that tend to happen here. One are false positives, basically labeling a image pair as a mismatch when in reality the ground truth is they're the same person, or false negatives where you do the opposite and is more dangerous in actual applied situations. And the work that I'm about to show you was first presented at the Military Operations Research Society Symposium in 2022. In general, the results that I got closely aligned with the literature, and it's that people do well at matching face attributes that are most familiar to them. In cognitive science, this is what we called a face space model, and it's a reflection of what the typical face was around you while you were growing up, usually. And this is why getting information in participant demographics was important. But if somebody is not falling in that face space that's familiar to you, human face matching can be pretty biased otherwise. And we saw this in our results. Participants had a hard time matching images that they labeled as having a different demographic identity as them. Additionally, we also found that certain facial expressions and disguises, as well as time pressure, also causes issues. Compared to AI, though, it's interesting to see that people are fairly robust when it comes to some spatial orientation factors, like if there are differences in quality issues or if there are changes in the angle from which a picture is taken. But on the other hand, AI is more robust than people at those familiarity factors, granted that you have a diverse enough training data set. And this is really important and is a source of constant conversations in face matching applications or face recognition in general. Now, while AI can struggle with image quality issues or camera angle changes, they're not really that affected by social factors. Like if somebody is smiling, humans are more likely to say that it's a matching image. And they can perform face matching at a much faster rate. Okay, if we follow classical principles around automation, specifically Paul Fitz's Habba Mabba, or humans are better at, machines are better at, we might be tempted to design our work system to follow a case-by-case assignment. We make a human do the face matching if they're more likely to succeed, or the AI based on the same set of factors. I will note here that Paul Fitz himself is on the record as saying that this should not be taken as a design principle. Alas, it still happens to this day in how automated systems are designed. But what if we have cases like this? So before Real ID became a requirement for air travel, TSA officers in Arizona had to deal with driver's licenses that don't expire until you turn 65. So IDs that were issued potentially decades ago, they might have different standards for image quality, or the picture just has faded entirely. And you have to deal with wildly different trends in hairstyles and even makeup. I want to emphasize that this problem did not disappear with Real ID, which restricts you to only a set of certain IDs now. Passports still have a 10-year expiration period, and we know that a lot can happen to what we look like in 10 years. The point that I'm trying to make here is that those issues with image quality, hairstyle, and so on, they do compound. So it's actually not that straightforward who is more likely to succeed at a face matching task between humans and AI. And ID verification in transportation security, it's a safety critical task. That means ethical and legal requirements must be satisfied, meaning that we can't just solve this problem by creating better AI models or by training TSA officers to perform better. In reality, it is a joint human and AI task, and that is the perspective that we should start from in designing these systems. So in the next couple studies that I will show, I explored how human AI decisions are affected by differences in interaction level designs. So in this first study, I explored how sequential changes in decision-making interactions could affect joint human-AI face matching performance across easy and difficult face matching tasks. So what you're seeing here is the default in today's ID verification systems, where as soon as the TSA officer scans the IDs, they immediately see the live camera feed picture and the ID picture along with the AI recommendation. But this doesn't always have to be the case. More and more studies have found that by simply asking people to make an initial guess is actually helpful in influencing or increasing the likelihood that at the end of interacting with AI, they're going to make a better decision. And this is one of the first studies to explore this phenomenon in face matching, which follows what I call a deferral interaction workflow. And we did this in two ways in our team at COE. The first was by framing people as the default decision maker, where the final decision here is phrased as them either sticking to their initial choice or changing their decision. The second way was by flipping that framing and showing the human as having more of an authoritative role. So the AI recommendation here is presented as the initial choice, and the human is asked whether they want to intervene or not, considering the initial guess that they independently made. Based on a pilot study, I selected cases that were either mutually easy or mutually difficult for humans and AI, and together with our team, we made it so that people were in one of two of those deferral framings, human default or AI default, and only 25% or 75% of all decisions were structured as a deferral. So those deferral conditions were both between subjects conditions. Now, there are two results that I want to highlight here. First is a complex three-way interaction between interaction design, ground truth, and difficulty on performance levels. So what you see here are bar plots where the x-axis is the mean accuracy in face matching tasks, and each bar represents a unique combination of deferral rate, so 25 or 75%, and framing, human or AI default. And if you compare the highlighted bar there, the 75% human default against the others, you'll see that it's pretty distinct from the others. It underperforms across difficulty levels when you have cases that are mismatches, but it does significantly better than others when they're actually the same person. So the match cases here are the panels up top, and the mismatch cases here are the ones at the bottom. And this has some pretty interesting implications for design. For one, we can consider how impersonation cases are actually really rare at airports. But it's really common for people to have to undergo additional screenings that cause delays and stress just because they don't look like their ID pictures. And this is stressful not only for them, but also for the TSA officers who are interacting with them. The other interesting finding here is that people's trust in AI was actually not different between these different interaction design manipulations. And this is based on participant responses on the Gian-Bizantin-Jury checklist for trust and automation scale, which is the x-axis of this. And it's one of the more widely used scales for measuring trust in these contexts. So, does the design and evaluation of human-AI interactions help support trustworthy work systems? Three things that we can take away from here, and then I'll pause for questions. First, simply mapping what is the common strengths or common weaknesses of people and AI may not be enough. And that was exactly what we tried to do here, predict the overlaps between human AI strengths and weaknesses, see if that was going to be what people were also strong and weak at when they're working with AI. But in our case, it's possible that human and AI collectives have their own sets of strengths and weaknesses that are distinct from those individual levels. So it follows that we can't disentangle these collective level human AI capabilities from the way that interactions are designed. And last, and this is really relevant because we're in a time when human AI interactions are becoming commonplace even outside the workplace, interaction designs that target decision-making sequence and framing might be a way to influence appropriate decision-making with AI, even without changing people's trust in their AI counterparts. I'm going to pause here in case there are any clarifying questions, but this does have a direct tandem study. Seeing none? Okay, now I'm going to talk about kind of the flip case of this. Explainable AI, which is another design approach for improving system trustworthiness, and how we can use similar interaction-centered principles to better understand how XAI works. Now let's go back to the example again of ID verification gates. This time, though, I want to emphasize the scale of decisions that are being made here. So each TSO can make upwards of hundreds, even thousands of face matching tasks on a regular basis. And based on qualitative studies that I've done with TSA agents, it's really clear that disagreements with AI are normal for them. How do they resolve it, though? Well, making the right choice based on the literature to adopt or reject AI inputs is a matter of how well they understand AI capabilities. And this is usually referred to as trust calibration in the human factors literature. But as these AI systems become more and more complex, TSOs are not being trained to understand how they work fundamentally, at least the AI systems. But they're also still expected to incorporate AI insights when making these face matching decisions in seconds or maybe a minute at most. And this could be problematic when you, again, have to make lots and lots of these face matching tasks on a daily basis. Now, this situation speaks to a growing question in research and practice, which is how we can design work systems that are trustworthy because they support people's abilities to know when they can trust what is, in reality, a black box AI counterpart. Black box because they don't have easy access to the underlying processes or understanding at least of those as they make the decisions at scale. And so that tandem study that I mentioned earlier looked into face matching for ID verification again, but this time with XAI or explainable AI as the main interest of research. And for this, I redesigned the testbed that I showed earlier into a testbed called FaceWise. This builds on the previous testbed by only following that human default deferral condition where the human makes a decision first before they see the AI recommendation, and then the choice is whether they're going to proceed with their original choice or change it. And I worked with computer science PhD students to develop two functional versions of this. So on the left, you can see the control version that looks really similar to the testbed from the previous study. And on the right is the explainable AI version where the AI recommendations are shown with additional information. I might be getting left and right confused here, but hopefully you see what I mean. So now I want to formally explain what I mean by XAI. And it's in reality a design strategy where in addition to showing main AI outputs to users, there are also additional, usually post hoc AI-generated explanations to provide users additional information to interpret the main AI output with. So for example, here you have confidence ratings that are presented maybe to show an estimate of how reliable the AI is for this use case or for this specific decision. And the user could use that to interpret this difference in opinion that they had. Some other forms of that include, obviously, like written explanations or visualizations that show more process-oriented kinds of information on what may be most influential in how the AI recommendation came about. Now, this first analysis that I'm going to show you was published in the Journal of Artificial Intelligence Research in 2024, and you can scan the QR code there if you want the full paper. I'm also happy to send it to you. But together with fellow graduate students at the Center for Accelerating Operational Efficiency, I conducted an experiment where I went to 3 international airports in the Southwest US and asked 152 transportation security officers to help compare how their expert face matching decisions would change depending on which version of FaceWise they were interacting with, as well as potential differences in how they would say they trust in the FaceWise system. And at the aggregate level, what I found was that the XAI version was rated as more trustworthy, or was rated by the human as them having more trust in it. Again, I'm trying to make a distinction between trustworthy and trust here for a reason. But you can see this on the bar plots on the left, where the y-axis represents the mean range of responses on the Geon scale, which I also used for the earlier study. On the left in red is the XAI version, and blue and right is the control version. But on the other hand, there were no significant differences in average face matching accuracy, which we measured as the percentage of face matching tasks that TSOs got right, and that's on the y-axis of the right-hand plot. So for months, I wrangled with this question: why was the XAI version rated as more trustworthy, even when the accuracy results tell us that the presence of XAI components may not have been affecting how they were making their decisions in the first place, at least not at the scale of analysis that I'm showing here. And eventually I realized that that was exactly the problem I had. It was the scale of analysis. This figure is borrowed from Aaron Chu and John Lee's 2021 paper that identified 3 different time scales at which trust and teaming unfold over time through accumulations of interactions. And relationships here span days, months, maybe even years, which was obviously beyond the scope of this hour-long study. But at the situation level, which matched basically the 80 face matching tasks that we had in aggregate, that's where we were measuring these average measurements that I found only a significant difference for trust levels. But XAI works at the interaction level, especially for designs such as confidence levels, which change per decision. And even though those take only a few seconds to make, it requires a finer scale of observing trust calibration. So at the interaction level, one way we can think about XAI is it's just like a form of team communication. It's about getting the right information to the right person at the right time. And so what are things that are being communicated here? So first, because of that multi-step deferral structure that I mentioned earlier, TSOs will have an initial agreement or disagreement with AI, and that is shown to them as soon as they make that initial choice. But if they're interacting with the XAI version of FaceWise, then they're also given additional information, specifically confidence levels that change with every decision, that give them additional context so that they can interpret this information. And so I explored how the presence and absence of those XAI designs, as well as the extent of AI confidence, impacted decision-making trajectory. And each of these 4 plots here represent different trajectories, so from agreeing to disagreeing, disagreeing to agreeing, and so on. And the x-axis here represents AI confidence, which was from 0 to 100%, and the y-axis is the probability that each of these decision trajectories would take place relative to AI confidence. I do want to clarify here that only participants in the XAI version saw actual confidence levels. So control lines here, which are the dashed lines, they mostly represent a baseline for XAI effects. So the first thing I want to highlight here is that our TSO participants rarely switched from their original decisions. And you can see that in the probabilities on the far upper left corner over there. None of them were above 10% across levels of AI confidence. But decision switches, interestingly, were also where the presence of XAI, including the confidence levels, had the most interesting interactions with difficulty levels. So the probability for decision switches peaks at about 50% when you have easy cases. But when you have difficulty cases, it tends to plateau above that 50% mark. And when talking about cases where the TSA officers did not change their original decision, they became more likely to stick to their original choice for difficult cases if they originally disagreed, and to original agreements for easy cases. Now, to look at this even more granularly, I created structural equation models, specifically multiple indicator, multiple cause models, or mimic models. And I wanted to see how trust calibration as a latent variable, which is in the middle of this path diagram, is indicated by factors like final accuracy, as well as observable behaviors like decision switching and final agreement, which are at the bottom of this diagram. At the same time, I also wanted to see how trust calibration was predicted by the same independent variables, which are up top, and you can think about it like they're regression predictors.
Sorry, I have a very quick question cycling back on the experiment design. When you measure the trust, like what's the frequency of the trust sampling? Is it every X trials or is it just at the end? You're just trying to get a picture on which part of trust is being measured.
Oh, yes, of course. Thanks for that question. So in this study, or at least in this analysis, trust, at least responses on that Gian et al. Scale is not part of this analysis because we only measured that at the very end of the experiment. Yes. So what we're looking at here are the things that we can observe per decision. Thanks for that question. Okay, so two important findings here is first, decision switches, which we know to be relatively rare, they were actually moderately strong indicators of miscalibrated trust, which you can see given that negative coefficient for switching decisions there. But final agreement with AI was a positive but somewhat weak indicator that people are calibrating their trust. Why am I pointing this out? So this is worth exploring further because we can't always observe decision outcomes, accuracy specifically, in real-life face-matching tasks. When somebody is going through a TSA gate, we're not checking if they're actually the same person or not. But we can check whether somebody is whether a TSA agent is constantly switching their decisions or constantly agreeing with AI. And that gives us some ideas on how we might design these decision systems in a more dynamic way. And finally, to answer the question that led me to this entire rabbit hole, I found that at the aggregate level, working with the XAI version of FaceWise had placed a penalty on trust calibration. And you can see that from the negative 0.226 regression coefficient there. But AI confidence, which again is the scale from 0 to 100, has a positive 0.469 coefficient. Now, if you do the math, that means that about 50% confidence, that negative penalty of showing TSOs the XAI outputs actually cancels out, and you have a net positive effect. So what this shows us is that XAI can be beneficial, specifically AI confidence outputs, under the right circumstances. A potential application of this is we can use those interaction-centered measures like decision switching or agreement rates to create adaptive display protocols, such as when AI would be displaying its confidence levels versus when they do not. So, can the design and evaluation of human-AI interactions enable trustworthy work systems? 3 things to take away from this are that, 1, explainable AI does enhance perceived trustworthiness without necessarily impacting how people make decisions with AI at the aggregate level. But when we look at it at finer scales of interaction, these designs can help for as long as they're done under the right circumstances. And this supports the idea that maybe we should be pursuing more dynamic human-AI interaction design protocols. And finally, interaction-level observations like those switching or final agreements with AI can be used as potential supplementary measures for measuring people's trust calibration when they're in the field. And again, this is really helpful, especially when you have safety-critical systems where you can't second-guess or verify the quality of decisions that are being made. I'm going to be pausing here in case there are any clarifying questions. Yes?
Not quite sure I followed the latent variable model. If you can just kind of describe this a little bit. So it looks like all the arrows are predictors, and then if you just kind of, and then I might have a follow-up question there. So the latent variable is a trust calibration, and the other ones are predictors. Is that correct?
Yes, that's correct. So the trust calibration here is, you can think of it almost like a mediator or moderator variable, where all of the variables up top predict it, but trust calibration is not something that we can directly observe. So it's indicated, at least in perfect circumstances, by the accuracy of the decision. But in this case, we also looked at switching behaviors and final agreement as potential supplementary indicators of that trust calibration variable.
But ultimately, you're trying to predict trust calibration.
That's correct.
And it's a latent variable, but then these are kind of like switching, and these are indicators of that, because you mentioned the word mediators there. Is that correct?
Yeah, that's correct. So this is generally how these multiple indicator, multiple cause models work, is you have these latent variables that are predicted by a bunch of different variables. You work on structural equation models, so I guess I don't have to explain it that much. But at least in this case, this is almost like when you're doing confirmatory factor analyses for certain constructs like trust or workload or stress, and you have certain questions. These are kind of like those questions below here, these indicator variables. But in this case, they're more behavioral. They're not really Q&A type questions.
Okay, thank you.
Thank you.
Yeah, in this study, can you let us know among the decision change, like incidence, what the percentage is a correct change?
Okay, so this is actually where this model helps us understand this. So trust calibration, the latent variable here, was perfectly indicated by final accuracy because we had access to the ground truth. And so what that tells us is that when there's a perfect correlation between final accuracy and trust calibration, there is also a negative trend that's revealed by switching decisions. So when people made switching decisions, it's very likely that they were actually miscalibrating their trust and resulting in a wrong decision. And this actually made sense because our TSA agents were, again, trained experts. We also used convolutional neural networks that collectively they had, independently, they had at least a 75% accuracy at face matching. So when they would disagree with each other, it would make sense that, okay, there's a 25% chance that one is wrong, 25% chance that one is wrong. If there's a disagreement there, then it's very likely that, they're switching, then it's very likely that they're winding up at the wrong choice. That was a very convoluted way of saying that. But in general, switching resulted in poor decision making.
Okay.
Yeah, thanks for that question. Okay, any other questions? All right. For the sake of time, I'm going to be moving on to the final part of this, which traces back to right around when I completed these ID verification studies, is also when I started working in industry, and where I got to take part in developing some AI-enabled decision tools for use by actual decision makers in the field. And so I wanted to give a peek into how I applied interaction-centered design principles to create experimental test beds for my own dissertation work that could then be designed for and evaluated by user populations. Before that, though, I do want to highlight that there are decent guidelines out there that exist. They are usually geared for AI software engineers, though. Those that aren't, like Google's People Plus AI guidebook, tend to be pretty generic in a way that some studies have found that it makes it difficult for system designers to adopt these design principles and use them for specific operational domains. So specific operational domains that are safety critical specifically can have a hard time with this because what constitutes as trustworthy within a safety critical environment is very unique to them usually. A good example of this is in intelligence analysis, which is a safety critical task if you're doing it for national security. And so reflective of this nature, in 2021, some of our collaborators at AFOSR and DNI published the Multi-Source AI Scorecard Table, or MAST. And MAST itself was based on Intelligence Community Directive 203, which laid out a set of 9 standards for intelligence analytics. So our research team at the Center for Accelerating Operational Efficiency was interested in validating MAST as a tool for evaluating trust, especially how it was theoretically valid relative to other scales that are derived from more foundational models like John Lee and Katrina C's 2004 seminal model. But to do this, we needed an intelligence analysis testbed, which at this point none of us had previously created, so that we could test MAST as it was intended, as a system rating tool for actual intelligence analysts where they interact with AI systems in realistic task settings that are more natural language processing oriented. So our team sought to design the Reporting Assistant for Defense and Intelligence Tasks, or READIT. I wish I could say that I came up with that acronym. READIT's specific application was to help out intelligence analysts who need to scour content online and identify credible threats to national security. And because of the scale of social media posts out there, this safety critical task can't just be human only. It has to involve AI because there are millions of posts that get posted out there. But again, it can't be solved by just having better AI because you flag the wrong thing and automate an entire apprehension process or investigation, then you might waste resources or even worse. Personally, though, I saw this as an opportunity to create a design and evaluation technique that marries my human-AI interaction research with previously underexplored interest in product design and development. And this started when I saw that system trustworthiness is itself a design objective, which means that we can combine human-AI interaction principles with rapid prototyping techniques to create READIT. And this eventually resulted in the principles-based approach for designing trustworthy human-centered AI using the MAST methodology, or PAD-TIE-MM, which was published by AI Magazine last year. I also did not come up with the acronym. Those who are familiar with rapid prototyping and product design development will probably notice that these are familiar or fairly common steps, these 5-step framework. What's unique about this implementation of it is that I identify methods so that we could apply these highly specific trustworthiness concerns and use guidelines that are outlined in MAST, or use MAST itself as an evaluation tool while we're prototyping. And so, for the sake of time, I'm only going to be focusing on the more the more interactive components of this process. And I'll talk later about how this could be extended to talk about future research. But now I want to go back to the READIT use case where we set a goal to create 2 different levels of the MAST rating for our system. So I will show you 2 mock-ups of the system that was created with computer scientists, UX researchers in our team, and my group of human factors engineers. And the first one was a low MAST version of Read It, which was designed to exactly be just that. It was just to fulfill the basic functions of intelligence analysis. Say you have an intelligence analyst that's interested in social media posts about a new consulate in London. So the bare minimum AI system might just prompt them to input London consulate as a keyword, but it's a very one-way interaction because it will spit out a list of highly influential posts related to keywords and a summary of the overall sentiments around these posts. Now again, this is still very much a natural language processing application, but it only really satisfies a couple of these masked criteria that we wanted to rate the system for. So we also created a high-masked version of Read It that was deliberately targeted to have interactive features that target other masked standards. So for example, this version alerts the user if the keywords they used resulted in too much uncertainty, and it generates alternatives that are similar to more interactive search engines. I also designed this interaction concept where the user can click a View Details option and they can hover over raw social media posts and see how maybe there was further processing involved, like translations, correcting of typos, and so on, as well as the integration of some dynamic visualization concepts like word clouds that would help analysts identify additional keywords they should consider or potential red flags. And this ultimately let us target a wider range of masked standards, which, again, those are mock-ups, what I showed you earlier. They were not the functional systems themselves, but they became a reference for us to design our functional test beds using a general population evaluation that we conducted in Amazon MTurk. And that resulted in 2 versions of a system that we eventually called Read It 2.0, which was used to evaluate masked against theoretically derived scales and accomplish the reason why we were trying to design Read It in the first place, which was with actual intelligence analysts in a simulated intelligence reporting task. Now, a couple interesting things here is that the original general population mass ratings actually predicted the eventual expert population ratings for the system. And it tells us that we can potentially use this model to have a low-cost, shortened time frame for designing these experimental test beds. And I'm happy to say that this method has been extended to other domains beyond intelligence and analysis, and that actually includes face matching. So the face-wise versions that I showed earlier with XAI was also created through this design process. 3 things that I want to take away from here is that interaction-centered design implemented this way lets us operationalize both theoretical and applied principles for what is considered trustworthy in work systems. And it also provides us a framework for potentially doing low-cost development of, again, those domain-specific test beds if we want to involve user population, or actual expert populations in our studies. And finally, again, at the end, it supports theoretical validation of these trustworthiness tools or evaluation tools that may have been originally derived from industry. Now, before I fully stop for questions, I'm just going to go over some quick directions that I would be really excited to take this research, including some ideas that have been inspired by ongoing work here at UW-Madison. First, I would love to extend this interaction-centered approach to ongoing efforts in simulating human interactions with AI. So I've recently begun working in DARPA efforts that focus on scenarios that aren't exactly teaming. That includes job negotiations with AI hiring managers, for example. And those are more social interactions, but I believe that in ISYE there are a lot more interesting operational contexts for which this can be used. Another area I would love to extend this to is the design of experimental test beds for more action-oriented work systems. So this includes search and rescue or driving safety, where it's not so much just about decisions that are being made, but also how they're being coordinated spatio-temporally. Again, I mentioned earlier that I'm working on large-scale evaluations at the Nellis Air Force Base for human AI decision systems, and I would be excited to apply methods that I am using to explore more human-in-the-loop optimization for areas such as air traffic control, hospital management, and emergency response operations, because these systems that are being used in the Air Force and earlier, based on my conversation with Jeff, also in the Navy, are really large-scale dynamic assignment and resource allocation problems that could be investigated with human decision-making considerations. And finally, there are many existing AI standards that could be adapted into domain-specific trustworthiness design frameworks like the pad thai methodology I showed earlier. And these includes domains that have established expert population linkages here at ISYE, including autonomous vehicle safety or clinical decision support systems. But there's also other frameworks like NIST's AI risk management framework and military aviation operations standards that are ripe for adaptation. In establishing my research program, I would initially target DoD and DARPA programs for independent proposals and collaborations with other faculty and my current industry partners. I know for a fact that the military is still very much interested in this kind of research. But as I expand out beyond military and national security domains, I would eventually love to explore opportunities to explore this in healthcare, with NIST, and potentially an eventual NSF career proposal for one of the programs listed here. Before I close, I do want to end this by acknowledging the many names. This is not an exhaustive list of people who have been foundational to my research over the last 6 years, particularly my advisors, Dr. Nancy Cook, and UW-Madison alum, Dr. Aaron Chu. And this is truly interdisciplinary work that I would not have been able to accomplish on my own. And it's a source of inspiration for how I would love to pursue future research like this with students, faculty, and partners across industry and the like. Thank you all so much for your attention today. We look forward to your questions.
Thank you for the great talk. So something I'm kind of curious about, right, is like your test beds were using Mechanical Turk. How would you suppose that it would change if we used, TSA agents or actual like intelligence analysts that have experience with, facial comparisons? Do you think that the measures that you got that would generalize, or do you think that there are other implications that we should take from it for that kind of domain-specific thing?
Yeah, that's a great question. So that pad thai framework that I showed earlier, it starts with those general population participants to help us iterate those testbed designs. But the objective is still to evaluate them with actual user populations. So FaceWise, for example, that was tested with actual TSA agents. We did field studies at San Diego International Airport, Vegas, and Phoenix Sky Harbor. And it did show that there are differences because TSA agents are better trained at actual face matching tasks. Same results with intelligence analysts, though that one, the use case was not really functional when we were making general population participants do the mock-up evaluations. But still, there was some predictiveness to how they were being rated at the end of the day. So maybe with some additional implementation of some of the stuff that all of you are doing here in terms of decision-making biases and so on, I would love to see how that would change as well. Thanks for that question.
Yeah, thanks, Mike. That was great. I have a question, sort of a probing question. So you had these things that were people, when they were presented with something called like the AI confidence, that this could impact, that potentially either impact, in some ways not impact when they changed and things like that. So what does AI confidence mean, and what does that number mean, and why should we believe it in the first place, I guess? Sort of
Gotcha. Thanks for that question, and I do want to clarify that. So those AI confidence outputs that are shown usually in XAI models like that, they're usually post hoc interpretations. So you have these two images that are being used as a basis for whatever recommendation an AI makes. But also, you can calculate cosine similarities between those two images and account how, okay, this resulted in a different or same recommendation. How does that translate into then how the user should be interpreting these results? So that's what the AI confidence levels there mean. Does that answer your question?
I guess so, but it's not a probability that it got it correct or that the AI is correct or anything like that. Like, does it have any interpretation as a probability?
Yes, thanks for that. So there is, I guess, what I would call an overlap. It's not a perfect approximation of the probability that AI got it right, because it's still an interpretive model of the AI's likelihood of getting something right. And this does have some correlation with overall AI performance on training data, but it's, again, it's implemented slightly differently in a way that there's enough distance from the training data that it's more an inference rather than an actual estimation.
Yeah, AI technology develop very fast. So today's AI performance is quite different from 1 year from now.
Yes.
So based on your study of human AI interaction, so what suggestions you will give for the AI developer, like if we want to improve human trust to the AI agent, besides we just drive for more accuracy, beyond that accuracy, so what factors you are suggesting, like people need to pursue in the AI development?
Yes, absolutely. So that's a great question. So on my end, that's why I really focus now on the system level trustworthiness. It's not just the human trusting in the AI, but the human AI system itself. Are they trustworthy when they start working together? And that's why some of those AI confidence markers and interaction structures that I showed earlier, AI could then also be used to implement more adaptive ways that information is presented to human decision makers, so that maybe they don't necessarily change how they rate the trustworthiness of a system using a Likert scale at the end, but they actually perform better. And ultimately, that's what trustworthiness is about. In terms of other considerations like, say, ethics and so on, some of that is pretty hard to codify, but there are other ways to consider, for example, how an AI might alert a human that, hey, historically, when you were doing the training, you didn't have that great performance with this demographic group, and so on. And that's just one idea that I'm thinking of as a potential application for this. But it's going beyond the individual AI outputs and incorporating AI into how it would shape the interactions that a human might have with it. Thanks for that question.
But I think we have a class coming in here, so I think we'll have to end. But like Mike said, I'm sure he's happy to answer additional questions, hopefully either in meetings or over email. But just wanted to say one more time, give us a chance to thank Mike for his time as a talk.
Thank you so much, everyone. Oh,
Token of our
thank you
appreciation
so much.
for visiting us.
It was really kind of you.
Yeah, thank you. That was wonderful.